All right, in this video, I want to talk about one solution to Maxwell's equations that's particularly interesting. And by a solution to Maxwell's equations, I mean that it is a solution to all four of Maxwell's equations. It satisfies each of the four. And to give you some idea behind the motivation to this solution, I'm going to give you a very heuristic example, which is that if I have a changing B field, if I have a changing B field from Faraday's law, we saw that this would induce an E field. And if in turn that E field changes, that, according to the Ampere-Maxwell law, can induce a B field. And so the idea is that maybe there could be a cycle here where a B field creates an E, which in turn creates a B, which creates an E. And this is very roughly the idea behind electromagnetic radiation. So let's talk about the specific solution. What we have is, imagine a region of space. Your book calls it a slab of space. And outside of the slab, E and B are 0. But inside the slab, E and B are non-zero. And it turns out if you choose E and B carefully enough, and if you choose the direction of propagation carefully enough, that this is a solution, this can be a solution to Maxwell's equations. So what is going on that's interesting here is that this slab, this area where the electric field and the magnetic field are non-zero, must move to the right. It must move to the right. Well, to the right because I drew my velocity arrow to the right, but it must move. It cannot stay put. So this is, if you like, this is like a pulse on a string. So the string is relaxed over here. It's just straight. The string is just straight over here. But over here, I've got a pulse in the string. And that pulse is going to move to the right. So I mentioned you have to choose E, B, and V appropriately in order for them to solve Maxwell's equations. And so here's one possible configuration. And that is to have a uniform electric field pointing towards the top of the page inside of our slab. Again, it's still 0 outside. Inside, it's pointing up, and the magnetic field is coming out. And this slab propagates to the right. So the relationship between E, B, and V we will make concrete in just a minute, but this is one possible orientation that will solve Maxwell's equations. So it's pretty straightforward to show that Gauss's law for electricity and for magnetism are satisfied here. So Gauss's law for electricity, I can draw a Gaussian surface inside of this slab, and you see that the electric field both enters and leaves that Gaussian surface. So the net flux through the surface is 0, therefore the charge enclosed in the surface is 0. And that's exactly what we have here, is there are no charges in this slab, just an E field and a B field. As for magnetism, it's the same argument. I draw a Gaussian surface inside this slab, and I have the magnetic field as both entering the box from behind and leaving the box coming towards us. So the net flux through the box is 0, which is what Gauss's law for magnetism demands, that flux must be 0. Okay, so Gauss's laws are pretty straightforward, so I want to move on to Faraday's law now. So with Faraday's law, I have this electric field inside the slab. And I'm going to draw my loop so that some of it is inside the slab and some of it is outside the slab. Now, if this slab is moving to the right, like I claimed it must, then the amount of magnetic flux passing through this loop must be increasing, because as this thing shifts to the right, so here our slab is shifted to the right, and this side has to shift as well. I'm going to pretend it was a wider slab. Okay, so the left and the right side of the slab shift the same amount. And what is that amount, by the way? Well, if it's moving with the velocity v, then it's going to be v times whatever the time interval was. That's how far it has shifted, both here and here. And so you can see before we had this amount of flux. But after it shifted, now this and this lie inside of the slab where we have a magnetic field. So the flux has grown from just this to all of this. Okay, so this region right here is the added flux as a result of this slab moving to the right with the velocity v. So how much flux was added? Let's label the dimensions of my rectangle here. I'm going to say it has height h and width w. Okay, so what's the area of this part that was added? So delta phi b, the area of this is going to be h is the height times the width of this, just this region that was added to my flux in this time interval, which was v delta t. So h v delta t is the area of this region times b, where again I'm using A times B for the magnetic flux. Okay, so the change in the magnetic flux is equal to this amount being added in a time delta t. And so then the change per time, which we're going to use as the delta t goes to 0, this is going to approach the derivative. Well, if I divide by time, I lose this delta t here, and I get hvb. Okay, so I've rewritten Faraday's law here. So you can see here, I have already calculated d phi dt on the right-hand side of Faraday's law, which is equal to hvb. Now I need to calculate the left-hand side of Faraday's law, which is the integral of E around this loop. Well, E, go ahead and extend things over a little bit. E is perpendicular to this edge of the loop and perpendicular to this edge of the loop. So that's E.dl is 0 for those edges. This edge of the loop is still outside of where the electric field exists. So there's no electric flux or no electric field here. So the only piece that contributes to this integral around the path, around the entire loop, is this piece right here, which is going to be h times the electric field. So the left-hand side looks like E times h. And so now equating the left-hand side and the right-hand side, we have EH equals HVB. We're going to cancel the V's. Cancel the H's when we equate these, and we get that E is equal to VB. Okay, so this is result number 1. That's going to be very useful. And that comes from Faraday's law. All right, next we're going to use the Ampere-Maxwell law. Okay, so here's the Ampere-Maxwell law. And there is no current in our problem, so this term is 0. And so it simplifies to mu naught epsilon naught times the rate of change of the electric flux. Okay, so back to our slab. It's moving to the right with a velocity v. Electric field is pointing towards the top of the page. So if I want to draw my Amperian loop so I get some electric flux through the loop, I'm going to have to draw it perpendicular to E, which is going to look like, from the side, it's going to look like just a straight line like this, but remember it's a rectangle, so this is the side view. From the top, now we're looking down on it from above. E is coming at us now. And our loop is a rectangle. Okay, so this is the top view. And both of these are the same Amperian loop, just one viewed from the side, one viewed from the top. Okay, so we're going to find d phi e dt very similarly to how we did it with the magnetic flux. So as my slab moves to the right, the distance velocity times delta t. I had this much flux before, but then I've added this flux. So this is the added flux as a result of the slab moving to the right, and more of my Amperian loop being inside of the slab as a result. Okay, so this is delta phi E. So delta phi E over delta T is, so what is the area of this rectangle right here? So again, I'm going to give this a height h and a width w. So I've got a height h times a width of this rectangle is v delta t times the electric field. Again, area times field, and all that over delta t. So the delta t's cancel, and we have that the right-hand side, d phi dt, is as delta t goes to 0, and the limit as delta t goes to 0, I have HVE. Just to back up to Faraday's law real quick, there's a minus sign in Faraday's law that I forgot. I'm going to put it right there. But ultimately, I'm just going to take the absolute value anyway, the magnitude. So this equation is valid for the magnitudes. The direction we have to figure out, well, we can figure out separately. Okay, so back to the Ampere-Maxwell law, we have this equation for the rate of change of the electric flux. So we found the right-hand side of our equation. Now we need to find the left-hand side by integrating B around our loop. So remember, B was pointing towards us when we were looking at it from the side. So now when we're looking at it from above, it's pointing this way. And the analysis, the integral is very similar as before. As I integrate around this loop, the contribution here is 0 because it's perpendicular to B. B is 0. So the contribution of all three of these sides is 0. The only contribution to the integral is B times H. So the left-hand side is going to equal B times H, whereas the right-hand side is mu naught epsilon naught times this rate of change, mu naught epsilon naught times HVE. All right, and so equating these, the H's cancel, and I get B equals mu naught epsilon naught VE. So this is the second important equation. And now if I summarize everything that we've done so far, we've shown that this moving slab with non-zero electric and magnetic field satisfy Maxwell's equations. And we've developed two relations that must be true. One is that E is equal to VB. Again, these are magnitudes. and the other is B equals mu naught epsilon naught VE. And let's combine these equations and solve for V. Okay, so we've shown that it satisfies Maxwell equations if these relations are true. Now let's combine them. I'm going to take this value for E, which is VB, and I'm going to put it right here. So then I get B equals mu naught epsilon naught V, that's this part, times E, which is VB, so I get V squared B. The B's cancel. I'm left with a 1 on the left-hand side. And so V squared equals 1 over mu naught epsilon naught. And this implies that V is 1 over the square root of mu naught epsilon naught. And now if we plug in these numbers for mu naught and epsilon naught, what do we get? We get 3, because remember these are constants, we get 3 times 10 to the 8th meters per second, which is the speed of light. So this is a remarkable accomplishment. Maxwell was able to, through fundamental principles, arrive at a prediction for the speed of light based on 2 constants that could be measured in a lab during his day. And the speed of light was also known during his day. And I mentioned earlier that they didn't have the ability to really test the modification he made to the Ampere law and give us the Ampere-Maxwell law. But with that modification, he was able to do this. And this was extremely convincing evidence that he may have been on the right track. He was able to predict the speed of light based on fundamental principles. And so back to this original cartoon flowchart thing here. This cycle is, in fact, a solution to Maxwell's equations. And this is an electromagnetic wave. That is the solution that we developed. In this case, it was a pulse. It only existed in a finite slab of space. So we have an electromagnetic pulse. But what we found here is that Maxwell's equations predict electromagnetic radiation. So not only did Maxwell unify electricity and magnetism, but he also brought radiation into it and showed that radiation, like light, X-rays, radio waves, and so on, are all just products of electricity and magnetism themselves.